Hello friends, I welcome you in lecture number 9 on normal probability distribution. In this lecture we are going to discuss one question which was asked in GTU Winter 2020 exam. So let's try to understand what is this question about. So the probability that an electronic component will fail in less than 1000 hours of continuous use is 0.25. Use the normal approximation to find the probability that among 200 such components, fewer than 45 will fail in less than 1000 hours of continuous use. So here the random variable under consideration is the number of electronic components who will fail in less than 1000 hours. We are given n equal to 200 electronic components, and for each electronic component there are two possibilities. Either electronic component will fail in less than 1000 hours or electronic component will not fail in less than 1000 hours. So here we first define random variable capital X as number of electronic components which will fail, number of electronic components which will fail in less than 1000 hours of continuous use. Less than 1000 hours of continuous use. So if we consider success as the event that, suppose success is the event that electronic component will fail, in less than 1000 hours of continuous use. In less than 1000 hours of continuous use. So if this event is considered as success, then it is given that probability of electronic component will fail in less than 1000 hours of continuous use is 0.25. So if we consider this event as success, then we are given the probability of success as 0.25. Probability of success is 0.25. So here our random variable is number of electronic components which will fail in less than 1000 hours of continuous use, and there are total 200 electronic components. So the possible values of this random variable X are 0, 1, 2 up to 200. Now for each electronic component there are two possibilities. Either electronic component will fail in less than 1000 hours of continuous use, or electronic component will not fail in less than 1000 hours of continuous use. So probability of success is given as 0.25 and it remains constant for each electronic component out of 200 components. So we can see this is the problem of binomial probability distribution. Here number of electronic components who will fail in less than 1000 hours of continuous use is a discrete random variable, and because all the conditions of binomial discrete probability distribution are satisfied, this is a problem of binomial probability distribution. Okay, so here capital X is a binomial random variable with n equal to 200 and probability of success P equal to 0.25. Now we are asked to find the probability that among 200 such components, fewer than 45 will fail in less than 1000 hours. That is, we are asked that less than 45 electronic components will fail in less than 1000 hours of continuous use. Now since x is a discrete random variable, this is equivalent to probability that x is less than or equal to 44. Now if we use binomial probability distribution, then we have to go adding up to probabilities starting from x equal to 0, x equal to 1, x equal to 2 and so on up to x equal to 44. So this is very much time consuming. We have to do 44 or 45 number of calculations because we are not having binomial probability in the table for n equal to 44. Binomial probability tables are not available for this big number of trials. So this is not advisable to use binomial probability distribution here. So this is the reason why they have assumed that use the normal approximation. So we have discussed in lecture number 6 that when we have to use normal probability distribution to approximate binomial probability distribution. So we have discussed in that lecture that if n into p is strictly greater than 5 and n into 1 minus p is also strictly greater than 5, then we can approximate binomial random variable by normal random variable, or we can use normal probability distribution to approximate binomial probability distribution if n into p and n into 1 minus p both are greater than 5. Some authors consider this condition also, so both are valid. Okay, in some books you will find this condition to approximate binomial distribution by normal distribution, so both are valid. These are not very strict rules. You can use either this one or this one as per your convenience. So here if we check what is n into p and n into 1 minus p, n into p is nothing but 200 into 0.25 which is nothing but 50. Okay, we can see 200 into 25 by 100, so this is 50 which is greater than 5. And if we consider n into 1 minus p, that is 200 into 1 minus 0.25, that is 0.75. This is 0.75 and this turns out to be this is going to be 200 into 75 divided by 100, so we can see this is 150, so it is also greater than 5. So we can use this normal probability distribution to approximate this binomial probability distribution, or we can calculate binomial probabilities using normal distribution, because normal distribution is good for approximating binomial distribution if n into p and n into 1 minus p both are greater than 5. In this problem it is already given that use normal approximation to find out required probabilities, so we don't need to show all these requirements. This is just for understanding. Suppose it is not given that use normal approximation, then also you have to do this problem using normal approximation, because here if we go by using binomial distribution, then we have to do calculations up to probability x equal to 44, so that is not advisable. It will take so much of our time. So here it is already given that use normal approximation to find out this probability, so we don't have to check even those conditions that n into p is greater than 5 and n into 1 minus p is greater than 5. It is already given in the question that use the normal approximation, so we can directly use the normal approximation. But if it is not given, then we should check whether we can approximate binomial distribution by normal distribution or not. and for that we must remember these two conditions. If n into 1 minus p and n into 1 minus p both are strictly greater than 5, then normal approximation is very good approximation to binomial distribution. So if we want to use normal approximation, suppose we want to approximate binomial random variable using normal approximation, then we have to remember this also. Suppose I am interested in this probability that capital X is less than or equal to X, where this X is a binomial random variable and I want to use normal random variable. So I have to add continuity correction. So if I have this type of event, capital X is less than or equal to X, and if I am using normal approximation, so this is approximately equal to probability that X is less than or equal to X plus 0.5. So I am adding continuity correction. So for more details about continuity correction, you can watch lecture number 6 on normal distribution. Similarly, if I have this type of probability, capital X is greater than or equal to small x, and if I am using normal random variable, I have to consider capital X greater than or equal to X minus 0.5. So whenever you are using normal random variable to approximate binomial random variable, remember that we have to use continuity correction. So if I have capital X less than or equal to small x, I will add 0.5 to this value of x. If I have this type of probability, capital X is greater than or equal to small x, I will subtract 0.5 from x. So with this in mind, we are able to do this question which was asked in GTU exam. So now we come back to this problem. Here we can mention that n into p is greater than 5, as we have done the calculations, and n into 1 minus p is also greater than 5. Therefore binomial random variable x can be approximated by normal random variable x. Now if we are using normal random variable, we have to find out mean and standard deviation or variance of that random variable, normal random variable. So we know that mean is given by n into p. So n is 200 into 0.25, so that is nothing but 50. And standard deviation, first we find out variance is given by n into p into 1 minus p, that is 200 into 0.25 into 0.75. So this becomes 37.5. Using scientific calculator I have written, but I am interested in standard deviation, so it is nothing but square root of variance, which is 37.5, and this is nothing but 6.12. So this x is a normal random variable with mean mu equal to 50 and standard deviation sigma equal to 6.12. Now we see what is asked. So use the normal approximation to find the probability that among 200 such components, fewer than 45 will fail in less than 1000 hours of continuous use. So now we are asked this probability that fewer than, or we can write probability that number of electronic components or simply components which will fail in less than 1000 hours of continuous use is less than 45. We are asked to find the probability that the number of components or fewer than 45 components will fail in less than 1000 hours of continuous use. So this is nothing but probability that capital X is strictly less than 45. Now here capital X is a discrete random variable, so this is equivalent to capital X is less than or equal to 44. Now using continuity correction, this is approximately equal to probability that normal random variable is less than or equal to 44 plus 0.5. So here this capital X is a binomial random variable. Now we are approximating it using normal random variable. So we are adding continuity correction of 0.5. So this is equivalent to probability that capital X is less than or equal to 44.5. Now here X is a non-standard random variable. So we standardize it by subtracting mu and dividing by sigma. So this is less than or equal to 44.5 minus mu over standard deviation. So this is now capital Z, which is less than or equal to, we have obtained values of mean and standard deviation. Mean is 50, standard deviation is 6.12. So this is equal to probability that Z is less than or equal to minus 0.90. So now we can use cumulative normal probability table to find out this value. Probability that Z is less than or equal to minus 0.90. So this is cumulative standard normal probabilities. Okay, we have this type of values in the table. Probability that standard normal random variable is less than or equal to Z, and we have Z equal to minus 0.90. So that we can write as minus 0.9 minus 0.00. So we look under the column of Z and we search for minus 0.9, and 0.00 is in first column. So minus 0.9 is here. So we look here, and this first column corresponds to 0.0. So this is the required probability, 0.1841. Okay, here we have 0.0 and here minus 0.9. So 0.1841 is the required probability. So here we write our answer. Just a minute. So it is 0.1841. So required probability is 0.1841. Probability that among 200 such components, fewer than 45 will fail in less than 1000 hours of continuous use is 0.1841. So this is the problem of binomial distribution, but we are not able to use binomial distribution because if we go using binomial distribution we have large number of calculations, but because this condition is satisfied we are able to approximate binomial distribution using normal distribution with mu equal to n into p and variance equal to np into 1 minus p. So in this way sometimes we can approximate binomial distribution using normal probability distribution, and we will remember this condition if parameters of binomial distribution are n and p, and if n into p is greater than 5 and n into 1 minus p is greater than 5, then normal distribution is good approximation for binomial distribution, and we can easily calculate binomial probabilities using normal probabilities. But we will remember this continuity correction if our binomial random variable has this type of event, capital X is less than or equal to small x, then we will add continuity correction. capital X is less than or equal to x.5. So here x is a binomial random variable, here x is a normal random variable, and this is also same. But if we have this type of event, capital X is greater than or equal to x, we will consider subtraction of 0.5. And if we have this type of condition, capital X is equal to x, then this we can rewrite as small x less than or equal to capital X less than or equal to x. So this is, if we use normal random variable, then this is equivalent to, for this we subtract 0.5, x minus 0.5 is less than or equal to x, because we have this type of situation here, capital X is greater than or equal to x, and for this we add 0.5. So always remember this continuity correction while approximating binomial probability distribution using normal probability distribution. So this is all about this lecture. I hope you like it. Thank you very much.